threaded spindles or screws are used in conjunction with sleeves that contain internal threads to form simple machines capable of supporting large loads. Threaded spindles are also used as fasteners to hold separate components of a mechanism together. These application uses are made possible by the inherent self-locking property of the threaded spindles. The self-locking properties arise from large frictional forces between the threaded spindle and the threaded sleeve, or nut, that is used in conjunction with the screw. These frictional forces vary due to parameters such as thread pitch, pitch angle, and the material used in the application. The range of applications for threads is boundless, and the range from bolts that affix components of mechanical systems to one another to threaded rods that allow for the raising and lowering of cargo bay doors or on commercial airliners. The efficiency of a thread in the case of a threaded fastener, such as a bolt, is measured as the amount of work out divided by the amount of work put into the threaded fastener. The remainder of the energy is lost due to the friction between the two materials. The amount of work out is the change in the potential energy of the threaded fastener relative to the threaded component the fastener is being threaded into. The work put into threading the fastener is the constant force required to rotate the fastener multiplied by the circumferential distance over which the force was applied.
The equipment for this experiment involved threaded spindles and nuts, and we're looking for the interaction between these two components. For the fasteners, we have a TR36 single-threaded spindle and a TR3012 dual-threaded spindle. For the TR36, we have three different materials: nylotron, gray cast iron, and red bronze. For the dual-threaded spindle, we just have gray cast iron. We also have weights that can be applied to the rotation plate. This one is 10 newtons, and the rotation plate weighs 20 newtons. Here's another 20 newton weight that can be placed on the rotation plate. Also, there's a spring force meter that can be used to measure force associated with the rotation of the spindle. In order to conduct the experiment, we start out with a single nut. Let's choose the nylotron nut. We place it in the collet and adjust the set screw firmly so it does not move. We'll then take a threaded spindle and thread it into the nut. Afterwards, we can use the spring force meter and attach it to this loop. Then we'll wind it around the rotation plate. Being careful to make sure that you don't affect the acceleration. What you want is a constant velocity as you pull. You can get your reading at a constant velocity, but if you cause acceleration, then that will cause error in your reading. After you get the first reading for just the rotation, the weight of the rotation plate, which is 20 newtons, you can add weight and repeat the process. Do this for every combination of weight in every nut, and afterwards you can change the spindle to the dual-threaded spindle and try with gray cast iron for a dual-threaded spindle.